Let's take a journey through the chemical logic of the citric acid cycle, going over the types of reactions that are occurring in each step, why it makes sense that these reactions are happening the way that they do, and at the end of the day, how this TCA, this tricarboxylic acid cycle, is able to serve as such a great resource for your cells to be able to interconvert molecules, to be able to generate energy from the fuel that you eat, all these great things. It's happening because of some really cool chemistry. Unfortunately, there's not time to go as deep into the chemistry in my classes, so you get to hear about the chemistry here, and so hopefully this nerding out will at least amuse someone. So let's dive in. The citric acid cycle, if we think about it as a cycle, for each turn of the cycle, we're going to be losing 2 CO2, generating 3 NADH and 1 FADH2, and then generating 1 ATP or GTP. We take a 2-carbon compound, the acetyl group of acetyl-CoA, we mash it with a 4-carbon compound, oxaloacetate, get a 6-carbon compound, citrate. We lose 1 carbon, we get a 5-carbon compound, we lose another carbon, we get a 4-carbon compound, and then we rearrange that 4-carbon compound to get us back to this 4-carbon oxaloacetate, which we can join in with another acetyl-CoA. So we're kind of losing 2 carbon dioxides. So 2 carbons as carbon dioxide. That's a really oxidized form of carbon. So these are going to be oxidations. We're generating NADH. In the second half of the cycle, we're not losing any carbons, but we're rearranging things. We're oxidizing things. So we're going to be generating more NADH as well as FADH2. We can enter at any start place in the pathway and then join in. And so if we put an alpha-ketoglutarate in over here, it'll turn out to generate an oxaloacetate. And if we've got oxaloacetate, well, now we can join it with an acetyl-CoA. We'll go quickly through all the steps, and then we'll dive deeper into the chemistry that's happening. So we have that 4-carbon oxaloacetate, and we have our acetyl-CoA. An enzyme called citrate synthase is going to combine them. And so this is a condensation reaction. And it happens through this intermediate Citriol-CoA. So when I show these things in brackets, those are going to be intermediates that aren't actually leaving the enzyme's active site typically. They're just going to be these transient, highly reactive intermediates that are then going to react inside the enzyme's active site to give you the final product. And so you often don't see them listed because they're going to be these kind of intermediate compounds that you're not really going to see. But they're really important for helping you see the chemistry that's going on. So we've got our oxaloacetate, which is 4 carbons, and our acetyl-CoA, which is 2 carbons, if we don't count the CoA part. We'll talk more about the CoA part later, but for now, just kind of think that it's this handle that's attached there. What's going to happen is that this methyl group is actually going to get deprotonated and attack this carbonyl carbon to form this Citriol-CoA. So we've still got that CoA attached. You might think, oh, we're going to swap out this CoA and stick this carbon on here. But no, we're actually going to take this carbon here for reasons that we'll talk about later, because it has a ketone group alpha to it. It's going to be more acidic. We can deprotonate it, and then it'll attack this carbonyl carbon and generate this Citriol-CoA. The CoA is still attached. Water's going to come in, and it's going to hydrolyze that CoA off. And so in its place, you're going to have a carboxylic acid. Then you already had 2 carboxylic acid groups. So now you've got 3 carboxylic acid groups, hence the tricarboxylic acid cycle, or the TCA. We also can call this citric acid, and so we have the citric acid cycle. So we've got citrate now. And now what are we going to do with it? What we're going to do with it is we're going to swap things around a little. So when we just move the positions of things in a molecule, we call that isomerization. And so we have an isomerase, an enzyme called a aconitase, that's actually going to do this isomerization. So you can see that if we think about our goal, we're going to ultimately lose this carbon dioxide and lose this carbon dioxide. We're not going to lose carbons from the acetyl-CoA this first turn of the cycle. We'll lose those carbons in future cycles. In this first turn of the cycle, we're just going to lose the carbons that were there from the oxaloacetate. So we're going to lose this one, and we're going to lose this one. First, we're going to lose this one. And this one right now, it's got a hydroxyl group right here, which is not going to be very easy to decarboxylate this, therefore. And so what we're going to do is we're going to shift that hydroxyl group over. We're going to shift it down a carbon. And the way that we're going to do this is we're first going to remove water, and then we're going to add water back in. So we're going to remove water, and that is going to give us this double bond, and then we're going to add water back in. We're going to add it in a way that the hydroxyl group ends up on the carbon that next to it rather than on this carbon. So we're isomerizing is the overall effect, but we're doing it by first dehydrating it and then rehydrating it. So we're taking out water and then adding in water. So there's no net use of water, but it does happen through this dehydration-rehydration mechanism. And this intermediate is going to be cisaconate. And we'll talk more about why this is possible when we get deeper into the chemistry. But for now, we have this isocitrate, and so we still have 6 carbons, and we want to now get rid of one of those carbons as CO2. We're going to specifically get rid of this middle carbon here. So we move the hydroxyl group away from it, and now we're actually going to get rid of it. And so how we're going to do this is through oxidative decarboxylation. We're going to oxidize this hydroxyl group to form a carbonyl. And so we're forming a ketone that is in the beta position to the carboxylic acid that we want to decarboxylate. So we want to remove this, and we've got a ketone in the alpha beta position. As we'll discuss later, this is going to be favorable to decarboxylate. And so we set ourselves up to be in this favorable condition where it's not too hard to remove that CO2. And so in order to get that actually to be a ketone, we oxidized it. And so we're going to be oxidizing it with NAD+ and generating NADH. This is happening in the mitochondrial matrix so that NADH can now go to the electron transport chain and pass its electrons off through complex 1 onto Q and use those to make ATP. So this is going to be your first place where you're actually kind of going to be generating some energy, but you're generating it indirectly by first generating the NADH, passing the electrons from the isocitrate onto NAD+ to give you NADH, and leaving you with this alpha-ketoglutarate. And this was happening through this intermediate oxalosuccinate. So now we've got this alpha-ketoglutarate, and it's 5 carbons. Now we're going to lose a second CO2, so we're going to lose another carbon to leave us with the 4-carbon compound Succinyl-CoA. So note that we're now introducing a CoA, so another CoA. And we have to do this because right now we don't have an beta keto acid, but we have what is an alpha keto acid. So we've got a ketone in the position that is alpha, so it's right next to the carboxylic acid we want to remove. This is going to be harder to decarboxylate for reasons we'll discuss later. And so when we have something like this, we have this alpha keto acid, we're going to need to use a more complex, since that's why this is called alpha-ketoglutarate dehydrogenase complex. And it will see that it's going to be very similar and actually share some parts with the pyruvate dehydrogenase complex. So pyruvate 2 is going to have a ketone, it's going to have an alpha keto acid. And so we're going to be using one of these complicated complexes that's going to be using CoA. Whereas for isocitrate dehydrogenase, we didn't have to use the CoA because we had a beta keto acid. And so we'll get more into the chemistry later. But for now, just know that we're doing this alpha-ketoglutarate dehydrogenase complex. And what it's doing is it's going to be taking this 5-carbon alpha-ketoglutarate and making the 4-carbon Succinyl-CoA, producing NADH along the way, releasing CO2, and it requires a CoA. And the CoA is going to get stuck on in the place where that carboxylic acid was. So you can think about kind of swapping this carboxylic acid for that CoA group. And now we've got this Succinyl-CoA. The next step is going to be to actually remove that CoA group and replace it with a phosphate group, and then remove that phosphate group and stick it onto GDP. So it's going to be a series of pass-offs, and so let's take a look at what's going on. We have this 4-carbon Succinyl-CoA, and again, I'm not counting the CoA carbons. And the S is just showing that CoA is attached through a sulfur linkage, a thioester linkage. What Succinyl-CoA synthetase is going to do is it's going to take an inorganic phosphate, and it's going to use that inorganic phosphate to basically chop off the CoA and replace it with the phosphate group. So it's going to phosphorylate the Succinyl-CoA to give us succinyl phosphate, releasing the CoA group. So we're not actually using the CoA on net, like the CoA comes in, the CoA comes out, and leaves us with the succinyl phosphate intermediate. We want to get the succinate. Now, succinate is going to not have that phosphate group. And so where's that phosphate group going? Well, the phosphate group is going to be transferred onto GDP to give us GTP. Technically, it's a phosphoryl group that's getting transferred, so a phosphorus and 3 oxygen molecules. And so this leaves us with the succinate molecule as well as this GTP. In some cases, you go from ADP to ATP. It depends on the isoform that's being used and the species and things like this. At this point, we're left with the succinate molecule. And note that succinate is symmetrical. Up until this point, your cells, the enzymes and everything were able to tell apart the carbons that came from the acetyl-CoA and the carbons that came from the oxaloacetate. And so if you were to do like metabolic tracking, you would be able to tell them apart. At this stage, however, you can't. And so this is going to be equivalent to this, and this is going to be equivalent to this. And so whether or not you lose carbons that were there from the oxaloacetate or carbons that were there from the acetyl-CoA, the next turn around the cycle is kind of like a 50-50 chance, depending on whether this flips or not. But yeah, more on tracking elsewhere. But right now we've got this 4-carbon molecule succinate. Our next step is going to be to dehydrogenate it. And so don't confuse dehydrogenate and dehydrate. Dehydrate is to remove water. Dehydrogenate is to remove hydrogens. And so when we're removing hydrogens, that's going to be an oxidation reaction. Remember, oxidations are involving the loss of bonds to hydrogen or gain of bonds to oxygen typically. And then a reduction reaction is typically involving the loss of bonds to oxygen or the gain of bonds to hydrogen. And so in this case, what we're having is we're losing bonds to hydrogen, and these carbons are going to be forming this double bond. The oxidations that we've seen previously have been hydroxyl groups to carbonyl groups. The energy from transferring the electrons from these carbon compounds onto the NAD+ to give you NADH, that was a sufficient drive in order to make those reactions happen. There was a big enough gap in the reduction potentials between the carbon compounds and the NAD+. But in order to make a carbon-carbon double bond, we're going to need a little more oomph. And so we're going to use FAD. And FAD, when you have FAD, it's going to be held in proteins and proteins. And so this succinate dehydrogenase is actually going to need to be holding on to that FAD. And the succinate dehydrogenase is actually complex 2 of the electron transport chain. And so this complex has to actually be embedded in that inner mitochondrial membrane where the electron transport chain occurs. And so this is happening in the inner mitochondrial membrane, and then these enzymes are going to be in the mitochondrial matrix. Although you also have versions of some of them in other compartments like your cytoplasm, because these enzymes can moonlight in multiple roles. An example is our malate dehydrogenase. We'll talk more about some of its roles later, but first we need to make malate to talk about it. Right now we have fumarate. So I've introduced this double bond, and now what we're going to do is we're going to add water to it. So we're going to hydrate it. So this is a hydration, again, not a hydrogenation, but a hydration. We're actually adding water. So we're adding water across the double bond, leaving us with the hydroxyl group. Now we're just one step away from getting that oxaloacetate that we need in order to bring in another acetyl-CoA. If we look at the difference between our oxaloacetate and our malate, we're just going from a hydroxyl group to a carbonyl group. And so this is going to just need an NAD+, generate an NADH. This reaction actually has an unfavorable delta G naught, and so the standard free energy change, if you were to mix equal molar concentrations of malate and oxaloacetate, the drive would be much towards going and making more of the malate instead of the oxaloacetate. But by keeping the oxaloacetate levels really low in the mitochondria, the cells are able to drive this reaction in the quote-unquote forward direction. So there you go. Now we're back to oxaloacetate, and we're ready to bring in another acetyl-CoA. To bring in the acetyl-CoA, if we were to start with pyruvate, such as we got from glycolysis, we actually first need to oxidatively decarboxylate the pyruvate. As mentioned before, this is going to be one of those more tricky decarboxylations because we are starting with an alpha-keto acid, and so we're going to be using one of those complexes. We'll get back to this step later on, but for now, just know that if you start from a glucose, only 2 of the carbons from each pyruvate are coming in. You have 2 pyruvates per glucose, So 4 carbons from glucose are going to be coming in. This carbons that are lost from this pyruvate to give you acetyl-CoA, if the pyruvate is coming from glucose, that's going to be corresponding to carbons 3 and 4 of your glucose. And so you're going to enter 1, 2, and 5, 6. These carbons are going to enter. And you have your acetyl-CoA, which joins to the oxaloacetate. You lose the CoA, you get the citrate. And so let's go through a little more detail. Starting with that citrate synthase. So as I mentioned, what's going to happen is that this methyl group is going to attack this carbonyl carbon of the oxaloacetate, forming this Citriol-CoA intermediate that then gets hydrolyzed to give you citrate. Let's talk a little about the chemistry of what makes this happen. Starting with some nomenclature. So if we think about our carbonyl carbon, we can number the carbons next to it using Greek numbering. And so the carbon right next to it would be your alpha, then the beta, gamma, and epsilon. Our focus is going to be on the alpha and the beta position. So the alpha is the carbon right next to your carbonyl, or right next to your ketone, right next to your carboxylic acid, depending on your perspective. And then the beta would be the one that was 2 away. If you have a ketone that is in the beta position of a carboxylic acid, so we have our carboxylic acid, this would be our alpha position, and this would be our beta position. We have a beta keto acid with the ketone in the beta position to the carboxylic acid. This is going to make it so that this carboxylic acid group is going to be easier to decarboxylate. So it's easier to remove this. And we'll talk more about why this is in a minute, but it's going to be easier to decarboxylate when you have a beta keto acid than if you were to have an alpha keto acid. So if you were to have an alpha keto acid, you'd have the ketone on this carbon. And so that's what we saw with like pyruvate and what we saw when we had our alpha-ketoglutarate. And we'll get back to that later. Another consequence of the carbonyls, though, that we want to get into first is going to be the fact that the alpha carbon, the hydrogen on the alpha carbon, is going to be more acidic. So it's easier to remove hydrogens from the alpha position. And when you remove a hydrogen, you can form this highly reactive carbon. There's this negative charge, this lone pair, which is then going to want to go and form bonds. So we're going to deprotonate this carbon that is next to the carbonyl. So it's alpha to the carbonyl. And it's going to be more acidic, more able to be deprotonated because it's next to that carbonyl. Why is what's going to happen is that when you remove this, you're left with a carbanion. So we have this lone pair of electrons on a carbon, highly unstable. However, the electrons can be pushed onto the oxygen, and oxygen would much rather have electrons. So we do our arrow pushing, we take our electrons, we form a double bond between these 2 carbons, and then we push the electrons up as a lone pair on oxygen. So oxygen would much rather have these electrons. That's great, but not so great is we've got an enolate. So in an enolate, we have a double bond between 2 carbons, and then one of the carbons has an oxygen group attached. So an enol would be if we had a hydrogen here, and so an enolate is just the charged version of that. The oxygen's electrons can actually push down to form a ketone, and then push these electrons from this bond back onto this carbon to form a carbanion. This form is very unstable. However, it has resonance stabilization by being resonance stabilized with this enolate form. Neither of these are very stable, however, so this is going to go on the attack. This lone pair of electrons in your carbanion can now go and actually attack another carbonyl carbon. And so what can happen is that when we remove the carbon here, we now are then going to be able to attack this carbonyl carbon. And when we attack this carbonyl carbon, now we're going to be basically taking this, what was a carbonyl, and now we're going to have a hydroxyl group here. And this carboxyl group here is going to correspond to this carboxyl group here. This is going to be the Citriol-CoA. So we still have this CoA attached. And now we're going to remove the CoA by hydrolyzing it with water. And so we're going to take water, chop off the CoA, and in its place, we're going to be left with this carboxylic acid group. Quick note about the CoA. So it's easy to think about CoA, oh, it's just a few letters, but really it is this molecule that looks like this. It's derived from vitamin B5 or pantothenate. And then this is the thioester linkage. So when you see that S, that's indicating that it's attached through this thioester linkage. When you have linkages like this that involve sulfur, sulfur has a bigger atom. It's got a kind of fuzzier electron cloud. And so linkages to it are going to be weaker and easier to kind of change out. So even though the CoA was kind of temporarily stuck on here, we can easily just take water and chop it off and leave us with this tricarboxylic acid compound, citrate. At this point, we went from having 4 carbons, we had 2 carbons, and now we had 6 carbons. So citrate is going to be 6 carbons. We're going to rearrange things, lose one of them, lose another one of them, then rearrange things, oxidize things, get back to that oxaloacetate. And this is our first step where we're actually joining things together to make our citrate. It doesn't happen quite so simply. It happens through an enzyme. Of course, it happens through the citrate synthase enzyme, but it happens in this aldol condensation mechanism, which is pretty cool, and I will post a link. Next up, aconitase. So here we're doing the isomerization. We're switching things around. So we're moving the position of this hydroxyl group from here to here with this intermediate cis-aconitate, which had this double bond. And it had this double bond because we removed water. Note that here, this is actually a dehydration reaction. This is not a dehydrogenation reaction. This is not a redox reaction. We're actually removing a whole water and adding a whole water rather than just removing hydrogens. So we're removing a whole water, we're removing HO, and then the H. And so we're removing a water, but then we're adding it back on. So we're adding HO and we're adding H. And then this is going to allow us to have this hydroxyl group in a more ideal position so that we can more favorably decarboxylate this carboxyl group. So we can more favorably remove this. So now we've got this isocitrate compound, and we want to take this isocitrate compound and produce alpha-ketoglutarate. So we want to do this reaction. This gets us to thinking about why this is energetically favorable, which takes us back to thinking about alpha and beta keto acids. And so if we think about where the ketone is in relationship to the carboxylic acid we want to remove, we're going to be going from isocitrate through an intermediate called oxalosuccinate that is highly, highly reactive, so it doesn't leave the enzyme active site, which is why we show it in these brackets. And it's going to decarboxylate to give us our alpha-ketoglutarate. So the main thing is we're going from isocitrate to alpha-ketoglutarate, but we're doing it through this oxalosuccinate intermediate in this oxidative decarboxylation reaction. What we have here is we have this carboxylic acid group that we're going to lose from that oxalosuccinate is going to have a ketone that is beta to it. So alpha carbon, beta carbon. The ketone group is in the beta position in reference to the carboxylic acid group that we want to lose. This is going to be favorable to decarboxylate. Let's think about what would happen if you decarboxylated a beta keto acid. The electrons from this oxygen, so like one of these lone pairs, could go and form a double bond to this carbon. Now the carbon's got too many bonds, so the electrons that were forming a bond between this carbon and this carbon now come flow over here, which pushes these electrons up. And now you're left with an enol. So you've lost the CO2 and you've gotten an enol. Now in enol, you've got the double bonds between the carbons, the single bond to the oxygen, much less favorable than a ketone. And so what's going to happen is that you're going to have a drive to get back to that ketone form. And then that is going to make it so you've got this strong drive that's going to make this reaction overall very energetically favorable. So it's going to be energetically favorable to decarboxylate a beta keto acid. And that's why we can do it more easily. In order to do that, however, we first need to set ourselves up through the oxidation of this hydroxyl group to the ketone so that we have the beta keto acid that we can then decarboxylate. And isocitrate dehydrogenase is going to allow us to do that. And so you can see that you first kind of oxidize it. And then what's going to happen is you get that push, 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 and then you get that push off and release. And so you can see that you kind of have some stabilization by metal. So you have the electrons flowing back from the oxygen, form a double bond to this carbon. Carbon's got too many bonds. The electrons then flow to here, forms this enolate, and the enolate then grabs a proton and pushes back to the ketone form, which is highly energetically favorable. That was very favorable, but now we're left with an alpha-keto acid. So if we go back to our arrow pushing, which I love arrow pushing, we take our lone pair of electrons that are on this oxygen and we flow them back to form a double bond to this carbon. Now this carbon's got too many electrons, but it can't just take them and form a double bond to this carbon because this carbon is already full. And so it doesn't have anywhere to push the electrons onto. So what's going to happen is you're going to be left with one of those carbon ions, not favorable. And so that is not going to be a favorable reaction. So we need to find an alternative way. And the alternative way is going to be through a complex. And that complex is going to be fairly complex, and it's going to use this CoA. This complex, as I mentioned before, it has parts that are shared by multiple different alpha-keto acid dehydrogenase complexes. And so this is going to actually be showing you the one for the pyruvate, this pyruvate dehydrogenase complex. But whereas in the citric acid cycle, we see this alpha-ketoglutarate dehydrogenase complex. When we think about branched chain amino acid breakdown, so like isoleucine, leucine, valine, they're going to use a similar complex as well. These are all going to use this kind of multi-subunit protein that uses a couple of key cofactors, thiamine pyrophosphate, or TPP, and then lipoic acid. And so what happens is that first the alpha-keto acid gets decarboxylated in place of the carboxylic group that it lost. It kind of gets linked onto this TPP, and then it gets passed on to the lipoic acid that's bound to this enzyme. And then it gets passed from sulfur to sulfur in this through these like lipoic acid transfers onto the CoA group and leaves you with that CoA compound where you have the CoA in the place of the CO2. So if you see an alpha-keto acid, you're probably going to have one of those more complicated complexes, dehydrogenase complexes, that are going to be using the CoA. But if you have a beta-keto acid, then you can typically just do simple oxidative decarboxylation. And if you already have the beta-keto acid, then you don't even need to oxidize it. But the oxidation part is to get it so that you have a beta-keto acid. And the beta-keto acid is so unstable that it all happens in the context of a single enzyme. In this case, we're left with Succinyl-CoA. So remember, we lose the CO2 and we get the CoA stuck on in its place. And now we want to remove the CoA. And what you might think if you just look from Succinyl-CoA to succinate, it looks like all you're doing is kind of like hydrolyzing or something, but that's not what's going on. You're not just going to add water and chop off that CoA group. Instead, what's going to happen is that you're going to transfer a phosphate group onto the succinyl part in place of the CoA, and then you're going to transfer that phosphate group from the succinyl phosphate intermediate onto GDP to GPGTP. And so we take this, remember those links through the sulfur are going to be easier to swap. So we're going to swap out this CoA that's linked through the sulfur. We're going to swap it for a phosphate group. So we're going to take this inorganic phosphate, this PI, this orthophosphate, it's just free-floating phosphate group. We take it and we stick it on in place of the CoA. So the phosphate group replaces the CoA, and now you get the succinyl phosphate. And we're able to do this because of the weak linkages that sulfur forms, but because of those big loose electron clouds, it can't form those tight grips. Not as good orbital overlap and things. So we kick off that, and now we've got this succinyl phosphate. We want to get succinate, so we need to lose that phosphate. We're going to put the phosphate onto GDP to give us GTP. And technically, we're only putting a phosphoryl group, the phosphorus with 3 oxygens. We still have this oxygen, so we still have this carboxylate group, so we have this succinate. And the succinate is going to be symmetrical, so we can't tell apart this carbon and this carbon, or this carbon and this carbon, until we start doing things to it, and that make it not symmetrical. So once we're at this succinate, We can't tell apart the carbons that came from the acetyl-CoA that were coming, say, from your pyruvate, from your glucose. You can't tell those carbons now apart from the carbons that were already there from the oxaloacetate. The next step is to go from succinate to fumarate. All we're doing is introducing a double bond. We're introducing a double bond between two carbons rather than a double bond between a carbon and an oxygen. This is going to require more energy, and so FAD is going to be better for us than NAD here. FAD has a higher reduction potential, which means it wants electrons more than NAD+. At least typically, the actual reduction potential of FAD depends on the protein it's held in. But in this case, the FAD has a higher reduction potential than the NAD+, which means that if we pass electrons from a molecule, so say we pass electrons from succinate onto FAD, we get more energy release than if we were to pass electrons from that succinate onto NAD+. This leaves us with less energy to pass off to Q, which is why we don't pump protons when we go through FAD, but we do pump them when we go through NADH. You have the same amount of overall difference in reduction potential between your fuel source and your Q, but in this case, we're kind of using more of the energy for this CC bond formation. And so this succinate dehydrogenase, remember that's complex 2 of the electron transport chain. So this is embedded in that inner mitochondrial membrane right here. And the other TCA reactions are happening in this mitochondrial matrix. So now that we've introduced that double bond to give us the fumarate, the next step is going to be to add water. Remember, this is a hydration, not a hydrogenation. We're actually adding a whole water molecule. So we're adding an oxygen and 2 hydrogens. We're adding them across the double bond, and this is going to give us this molecule malate. Now, malate is one step away from oxaloacetate, which was the kind of start of our pathway. To get from malate to oxaloacetate, we need to oxidize it. Here, we're just forming a double bond between an oxygen and a carbon, rather than between 2 carbons. And so the energy that we get from transferring the electrons from malate to NAD+ is going to be enough to do this for us. This is going to give us this oxaloacetate. And now we are back to the situation where we can bring in 2 more carbons from acetyl-CoA in order to make citrate. This acetyl-CoA can actually come from multiple sources, but one of the common sources is going to be from pyruvate that comes from glycolysis. Although that pyruvate can also come from other sources, such as lactate, it can come from alanine, other amino acids, things like this. Now, pyruvate is one of those alpha-keto acids, so we've got this ketone group that is going to be alpha to the carboxylic acid we want to lose. Because it's an alpha-keto acid, we're going to lose it through one of those more complicated complexes that uses CoA, and it uses those cofactors like lipoic acid and TPP. This carbons that are lost from this pyruvate to give you acetyl-CoA, if the pyruvate is coming from glucose, that's going to be corresponding to carbons 3 and 4 of your glucose. And so you're going to enter 1, 2, and 5, 6. These carbons are going to enter. And so basically what happens is that in glycolysis, you end up splitting into 2 molecules, 2 3-carbon molecules, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. And these are interchangeable between one another. So they convert between one another, but then only the glyceraldehyde 3-phosphate carries on. If we look at pyruvate versus acetyl-CoA, the carbon that we're going to lose is this carbon here, which corresponds to the carbons 3 and 4 of your glucose. And so this carbon and this carbon are leaving before you even enter the TCA. So the ones that are coming into the TCA are going to be your 1, your 2, your 5, and your 6. But you can't tell apart 1 and 6 and 2 and 5. But 3 and 4 are lost before you actually get into the pathway. So we go from glycolysis, we split in 2, we lose carbons 3 and 4, and so now we have these 4 carbons that can enter into the citric acid cycle, but they're going to go 2 at a time in the form of this acetyl-CoA. And along the way, we've lost that carbon 3, 4. And now we're going to hook up right here to the top of our oxaloacetate to give us Citric-CoA, which will then hydrolyzed to give citrate. So those carbons 3, 4 are lost before we go into the citric acid cycle and leaving us with our 1, 6, and 2, 5. And so it's 1, 6 because those are, you can't tell them apart, and then 2, 5, you can't tell those apart because in glycolysis, you split into these two pieces that then become the same piece in a way. And so you can't tell apart your 1, 6, 2, 5, or 3, 4. But the 3, 4 are lost before you enter the citric acid cycle. And then in that citric acid cycle, the first turn of the cycle, you're not going to lose any of the new carbons you brought in from the acetyl-CoA. You're only going to lose the carbons that were already there from the oxaloacetate. And now if we think about what would happen the next cycle, well, this carbon is going to be lost and this carbon is going to be lost. So we're going to be losing one that's from the acetyl-CoA that we brought in the last cycle and one from the oxaloacetate that was 2 cycles ago. Things get more complicated when you think about the next cycle, but for now, just know that in that first turn of the cycle, you don't lose any of the new carbons you brought in. In the second cycle, you lose one of them. And in the third cycle, you might lose the other one, but it might be actually take you more cycles, depending on how things flip when they bind to the enzyme. But it's going to take you at least 3 cycles in order to get rid of those 2 carbons that you brought in from acetyl-CoA, like in terms of those exact carbon atoms. There are other ways to get oxaloacetate as well. So we can actually take pyruvate and we can carboxylate it to form oxaloacetate. So actually add carbons to pyruvate, go from 3 to 4 carbons instead of going from 3 to 2 carbons. This is going to be an example of an anaplerotic reaction. So it's a reaction that can actually regenerate pathway intermediates. This is going to allow us to then take out any of these molecules in the citric acid cycle and still enable the cycle to keep going. So we can take out, say, malate to go make glucose, and then we could add in oxaloacetate through pyruvate carboxylase. And then that would then allow this cycle to keep going. But acetyl-CoA cannot come in unless you already have oxaloacetate in there. So if you take something out of the cycle, you've got to put something in the cycle that's already kind of like in the cycle, not just the acetyl-CoA. You've got to add more than 2 carbons because each turn around the cycle, you're losing 2 carbons. So if you want to put in acetyl-CoA, you need to make sure that you've got the 4 carbons in there. And if you remove something but only put in 2 carbons, then you're going to be out of luck because all these intermediates, the smallest ones that we have are 4 carbons. So there you go, the citric acid cycle. Some cool chemistry going on, a lot of it involving carbonyl chemistry. And it's highly integrated into metabolism, serves as a central coordinating hub. It serves anabolic and catabolic roles, lots of interconversions, some really cool stuff. And so thanks for letting me nerd out.